All right. If not, I mean, we're really only going over one question, so you really don't need it too much, but if you do need a copy, I have it. All right. So last class, we were continuing the trig functions of important angles, sine, cosine, tangent, even the weird ones like cosecant, secant, and cotangent. We've been going over, and we did a lot of work with that. We were able to find any angle on the unit circle. We could take the sine, cosine, or tangent of those angles. And I think where we left off was finding sine, cosine, and tangent of angles that might not be on the unit circle. There's more angles than just the angles on the unit circle. And we even found the cosine of negative pi over 4. Okay, so we are able to find the angle or the sine, cosine, and tangent of negative angles as well as regular angles. And what I'm going to go over is one more example. We're going to find the sine of an angle that isn't negative, but it's also not on the unit circle as well. Okay. So 17 pi over 6 is an example of something that, well, it's not negative, but it's also like way off the scope of the unit circle. Oh. So 17 pi over 6. Does anyone remember what we did last class to find, like, to change that angle into something that we could work with? Good. We found the coterminal angles, which we found by adding and subtracting 2 pi, which was a full degree around the circle. So we're going to add, subtract 2 pi. Okay, so it seems like, oh, sorry, Miriam's here. Seems like if we added 2 pi, you could try it, but you're probably going to get an angle that isn't going to work very well. So I'm going to subtract 2 pi. Okay, 17 pi over 6 minus 2 pi. Okay, this is something that you can do in your calculator, but for this class's sake, I'm just going to do it by hand so we can all see how this works out. Okay, let's say I want to write this as 2 fractions being subtracted from each other. The first one's over 6, so let's just leave that over 6. How can we write 2 pi as a fraction over 6? 12 pi over 6, right? 12 divided by 6 is 2. So 12 pi over 6 is how I write 2 pi over 6. Okay, now that everything's over 6, we can subtract the 2. And we are left with, I think, 5 pi over 6. Does that sound right? So what we've done, we've taken 17 pi over 6, which isn't on the unit circle, and we've changed it to an angle that is on the unit circle, which is the same spot as 17 pi over 6 would be. Okay, so that means the sine of this angle is going to be the sine of 17 pi over 6. So let's do this. Sine of 5 pi over 6. Okay, taking a look at your unit circle. Okay, the reference angle is pi over 6. What is the sine of pi over 6? One half. Good. It's the y value. So you just look at pi over 6 and it should be the y value in there. You should get 1/2. Let's take a look. Is 5 pi over 6? Well, what quadrant is that in? 2. And is sine positive or negative there? Positive. Good. So this is positive 1/2. And that's our answer. That's all you got to do. Any questions on finding sine, cosine, tangent of funky angles like that? All right. I think we're all good with this. You should be good with those questions on the homework that ask you to find sine, cosine, tangent of like any sort of angle. So you should be pretty good with that. We're actually going to go to a new section today now. All right. So we have a new set of guided notes. Let me flip to them real quick. Oh my goodness. Here we go. Looks like this, and I will pass out these guided notes. All right. So we are going into uncharted territory here. We're going to do something different with sine, cosine, tangent. Yes, I feel like this is something that scares people because, well, I'll tell you later. But I promise you it's not that bad. And this is actually something I really enjoy doing. Like, I honestly can do this in my free time. And it's like actually kind of fun. But non-math majors might not think it's very fun, but I'll tell you why. All right. So before we get into this, the first thing I want to talk to you about is some notational things. Oh, wait a minute. I don't think did I mute myself on here? Yeah, okay. No, I'm good. Oh.
No, I thought I was going free.
Okay, I see why. It's the volume is like up on the computer. So oh man. All right, I think it's good now. Okay, yeah, I don't hear myself anymore.
Me either.
Okay, wait, I didn't share my screen now. Oh gosh. Oh no. There we go. There we go. Okay, now we're good. Okay. So before we go into anything, I want to talk to you about some notation. Sometimes we're going to take trig functions and like square them or cube them or take it to the fourth power or something like that. And you might like seeing this makes it kind of obvious that we're taking sine and squaring it. We're taking tangent and squaring it. Since sine, cosine, and tangent are used like a lot in pretty much everything, engineers will tell you that they use sine, cosine, tangent in literally everything that they do. Sometimes what we do is we'll put the square in a different spot. So we won't put parentheses around it, and we'll just put the square above the sine to just say that sine is being squared. Or even if there isn't a specific angle, we can just put the 2 up top. And all that means is we're taking tangent and we're squaring it, okay? So if you ever see this notation, that all it's saying is we're taking sine and squaring it, taking tangent, squaring it. Okay, so now that's over with. Let's talk about the fundamental identities. I know it looks kind of crazy. Don't freak out when you see this, okay? We have a bunch of different things called identities. And what these do is they kind of generalize properties of sine, cosine, tangent, cosecant, secant, and cotangent for any angle instead of just like, I don't know, pi over 3 or 7 pi over 6, okay? So let's take a look at some of these. Now, don't freak out. I want you to memorize all of these, okay? Now, you won't have to memorize all of them if you know the tricks to memorizing them, okay? So don't freak out. You will have to memorize these. Have to memorize all these guys, but I promise you it's not that bad, so don't freak out, okay? Let's just take a look at the reciprocal ones. I think we all have these sort of in our head already. Remember, sine and cosecant are kind of together. They're reciprocals of each other. Another way of saying reciprocals is that one is 1 over the other, okay? Secant is reciprocal with cosine, and cotangent is paired with tangent. So these two go together. These are what we call the reciprocal identities. Okay. Technically, there are 6 reciprocal identities. Remember, we only needed to memorize 3 of them, so 3 of them are up on the board, okay? Next, we have the tangent and cotangent identities. We have talked about the tangent one a bit, but it might be written in a different way. So let's take a look at tangent. I think when we defined what tangent was using the unit circle, we said that tangent was y over x, right? We took the y value, divided it by the x value. But y is another way of saying sine, right? Sine is the y value on the unit circle. X is cosine on the unit circle. Okay, so all this is saying is that tangent is the y value sine over the x value cosine. Okay, so this one definitely memorized. You probably have it in your head already because you know that y over x is tangent. Okay, going over to cotangent. This one's a little, I don't think we've seen this before, but you know that cotangent and tangent are paired together. They are reciprocals of each other. So all this is saying is that cotangent is the flip of tangent. So they just flipped over the cosine and sine. Okay. So taking a look at this, I guess you don't have to memorize the cotangent if you know what tangent is, because you can kind of get to it using the first identity. Okay. So far, all we really have to do is memorize the first 3. and maybe this one, but you should be able to get to the cotangent. That is. Okay, next one. We have the things called the Pythagorean identities. I know we haven't gotten to this yet, but let's just talk about what these are. Okay. What's the Pythagorean theorem? Good. A squared plus b squared equals c squared. Okay. Basically, what this is I wish I could talk about it more about how we actually get to these. But it basically is the Pythagorean theorem. I'll just give you a hint. When we have right triangles on the unit circle, we said that sine was the y value, cosine was the x value, and those are the legs on the right triangle. Basically, what this is doing is sticking it into the Pythagorean theorem. If you really remember, think back to the unit circle, we said that the hypotenuse was always 1. This is all we're doing. We're plugging it into the unit circle. If that doesn't strike a bell, just remember it looks like the Pythagorean theorem, and we have sine squared plus cosine squared equals 1. Okay. I think this one is the easiest one to memorize, so make sure you know this one. Okay. And the other two, you do have to know and be able to memorize, but let me give you a hint on how to get to these from the first one. Okay. So what I'm going to do is on the very bottom of my sheet, I'm just going to split it into half. Right? And let's just say the only thing I memorized was sine squared plus cosine squared equals 1. Okay. So all I did was do this. Sine squared plus cosine squared equals 1. Let's say I didn't remember the other two, and maybe I want to like do some stuff to get to the other two. Okay. What I'm going to do here is I am going to divide everything by the same thing. We can always do that with an equation. And the thing I'm going to divide by is, well, let's do sine first. Okay, and because everything's squared here, I'm going to divide not by sine, but sine squared. So taking a look at the first part of this, what is sine squared divided by sine squared? 1, right? You're dividing something by itself, you're going to get 1. Okay, so that becomes 1. What do you think cosine squared divided by sine squared is? Take a look at your identities. Let's take a look up here. Is there anything up here that looks like cosine over sine? Cotangent, right? But let's see, there's a big difference. One of them's squared and the other one's not, right? Well, cosine squared divided by sine squared is cotangent squared, okay? So cosine squared over sine squared, let's just write that as cotangent squared theta, okay? Finally, we have 1 over sine squared, okay? Anything up here look like 1 over sine? Cosecant. And since it's squared, what do you think it's going to be? Cosecant squared. Good. All right. Okay. So let's take a look at what we've done. We've started out with one thing that we've memorized. Sine squared plus cosine squared equals 1. And we ended up with, well, this guy over here, right? They're the same. 1 plus cotangent squared equals cosecant squared. So as long as you memorize the first one, you can always get to the third one. Okay. Let's talk about doing it in a different way. So let's say we still start out with sine squared plus cosine squared equals 1. And how about instead of dividing by sine squared, I'm going to divide by cosine squared. Okay. Now, what do you think sine squared over cosine squared is? Tan squared, good. What is cosine squared over cosine squared? 1, right? We're dividing something by itself, so that gets 1. And what do you think 1 over cosine squared is? Cosecant squared, good. Oh wait, is it secant or it's secant, good. Sorry, I get mixed up between the two too. So 1 over cosine is secant, so 1 over cosine squared is cosecant. Oh, sorry, secant squared. Oh my goodness. I'll just write it down. Whew. Okay. So let's step back here. We started out with sine squared plus cosine squared equals 1. We did stuff to everything, single thing in the equation, and we ended up with 1 plus tangent squared equals secant squared, which is actually the middle one on the chart. Okay. So as long as you know the first one, the first Pythagorean identity, you can figure out the other two pretty much by dividing by sine squared or cosine squared. Okay, so taking a look at this, I know I told you to memorize all of them. As long as you memorize the ones that I have highlighted, you should be okay with getting everything else. Okay. Any questions on the identities before we go on? Cool. Let's flip our page. Okay. Here's where things get, to me, really exciting. I really like questions like this. I feel like they're like puzzles. But I feel like when you look at this for the first time, it looks very scary. So when you go off to take a class called calculus, you will have to do questions where that involve sine and cosine. Okay. And you'll get at the very end, you might get an answer that looks like this: tangent, cosine. Okay. Now you hand it into your professor takes your test and he grades it or she grades it, and they look at it and they're like, oh, I'm going to take off a point because it's not simplified. Okay. And you're going to be like, oh, darn it. I should have went back to 140 and learned this. Okay. So this is where this sort of question comes up. Simplifying something that looks like this. Okay. I know it looks kind of already simplified. It looks pretty neat, but this is not simplified because, well, it has to be written as like one specific trig function in the numerator. Okay, so it has to be like sine or cosine or tangent. And if it's not one of these, it has to be like a constant, like 1 or 50 or 30,000 or something like that. Okay, so whenever you get a question like this that tells you to write each expression in terms of a single trig identity or a constant, all it's telling you to do is to take this and simplify it to like one thing, like a number or sine, cosine, tangent, something like that. Okay. I feel like these sort of questions are like, I don't know, like very hard when you look at them because a lot of students like don't know what to do first. Okay. It kind of reminds me of the SAT or the GRE where you take the question and it like tells you to do this, and unless you know the very specific trick how to do it, you can't answer the question. And in order to get the trick, you have to like buy the really expensive book that tells you how to do it. Luckily for this class, I will tell you the trick on how to do this. I found a good way on how to simplify these guys. And let me tell you what the trick is. Okay, you don't have to buy the expensive book on the GRE how to do this. Okay, so whenever you get a question that asks you to simplify the trig identity into a constant or a trig value, all you have to do is change everything into sine and cosine. This is the trick that works for me at least. Okay. So whenever you see this, I know it sounds like there's a bunch of things to do. You have all these different identities that you can work with. The trick here is to change everything into things that say sine and things that say cosine. This is because sine and cosine are really easy to work with, and there's a lot of stuff in our identities that use sine and cosine. Let me show you how to do something like this. So we have tangent times cosine, okay? What is that? Yeah, I'll look them up on Spotify. All right, so cosine's already there, so I don't have to change cosine into anything. Is there anything on the identities that change tangent into sine and cosine? Sine over cosine, good, right? If we look at our identities, this one says tangent is sine over cosine. So why don't I change the tangent into sine theta over cosine theta? Okay, and since cosine is multiplied at the end, I'll just keep it there. Okay. Anything we can do now? Yeah, we have a cosine up top and we have a cosine on the bottom. If you don't see that, you can always write cosine as cosine over 1, right? And since, well, the denominator and the numerator are the same thing, we can cross them out. And, well, it looks like we have just sine theta. So to do these questions, I know it looks crazy. I know it looks like there's a bunch of things that you have to do. If you change everything to sine and cosine, you should be okay. Let's do another one. All right. This one looks even more scary. And it is a little bit more work, but I promise you it's the same sort of process. Okay. We have sine secant over tangent. Lots of stuff going on. Okay. What we are going to do is we have a division sign. Let me just write that division sign so it's there. Okay. Let's see. We have a sine. Well, sine doesn't change. So, or sine isn't. Well, sine is sine or cosine, so let's just leave that as sine. Okay. Anyway, we can write secant as something involving sine and cosine. Good. Secant is, well, let's take a look. 1 over cosine. Yes. All right. Oop. There we go. Okay. So I changed the numerator into things that involve sine and cosine. Okay. Next we have tangent, which is sine over cosine. Good. Okay. Here's where I get confused. I look at this and honestly, I know it's a fraction over a fraction and I know I have to multiply by the reciprocal somewhere. For some reason, my brain does not comprehend what this is. Okay. The way I do this, and I know you might think I'm done for doing this, I'm just going to write sine as a fraction over 1, just so it makes it easier in my head to multiply the two things in the numerator. Okay, I know it sounds dumb. Okay, so what I'm going to do is multiplying across the numerators, I get sine times 1. So this becomes sine theta. The denominator says cosine times 1, which is cosine. Okay, this is all over sine over cosine. Okay, so I know that sounds kind of dumb, but for some reason it's easier for me to look at it like that instead of what was in blue. So that's all I'm doing there. Okay. Any ideas on what to do next? It is just one. If you don't see it, I guess we can keep change flip too. So if you see this as something divided by itself and you just want to skip to saying 1, totally fine. Let me keep change flip. Okay. So remember, keep the first fraction as it is, sine theta over cosine theta. We're going to change the division sign to a multiplication sign, and we're going to flip the last fraction over. Okay, once we're here, well, looks like we can cross a lot of things out, right? Cosine, cosine, sine, sine, and looks like all we're left with is 1. Okay, you didn't need to show that step if you saw it already, but sometimes I have to do it. Okay, so dang, it looks like we started out with sine secant over tangent, and that was actually equal to 1. Not that bad. All right. So we have 2 more on the back. Part D, I think we had a little struggle with last class, but I think we'll be okay doing it. So try C and D. If you're struggling on part D, don't worry. Do you want to take us through part C?
Yeah, so secant over tangent is just 1 over cosine and then sine over cosine. And then that I just keep change flip, which is 1 over cosine times cosine over sine, which is just 1 over sine. And then that's just cosine.
Perfect. One thing I do want to say is I see a lot of people ending at 1 over sine. That's technically not simplified. So the next step would be to go to cosecant. So if you see, like, I know it says like write it in terms of like 1 trig function. Technically, I see that that's what you're doing, but once we get here, what am I trying to say? Having the sine, cosine, tangent in the denominator usually isn't like the most simplified version because Perfect. All right. Any questions on C or D? All right, I think we're all good on this one. So I'm going to get myself set up. So I think let's flip over our page to the next set of examples, example 2. Okay. And we're going to talk about, well, a different type of question that we can see. Okay. So I told you about simplifying all these different things. Another thing that you could see in this class called calculus is maybe you want to represent one sort of trig function in terms of another. All that means is you want to like write sine, but instead of writing sine, you want to use like cosine or tangent or cosecant. Okay. So let's kind of read example 2. Alpha is an acute angle, and we want to represent sine of alpha in terms of cosine of alpha. Okay. All this is saying is I want to get sine on one side of the equation, and I want cosine to be in like the rest of the equation. Okay. So I want my answer to look like sine alpha equals something, and there better be a cosine in here. Okay. And nothing else. Okay. So just like the last sort of question where we had to simplify something, the trick is going to be something different. Okay, so there is a trick for these. Okay, and usually the trick for these is to use the Pythagorean identities. Okay, so you want to use the Pythagorean identities. Okay, so there's always a trick for these trig function identity things. And that's what makes it kind of fun because you like know what to do in the beginning and then it kind of falls out at the end. Okay, so I want to express sine in terms of cosine. Is there any Pythagorean identity that does that for us? Not quite. Let's take a look at the Pythagorean ones. The first one, right? And the first one says that sine squared of theta plus cosine squared of theta equals 1. Okay, so I'm just looking at things that use sine and cosine. Now let's take a look at the question. The question talks about sine of alpha, not sine of theta. So maybe in my Pythagorean identity, I'm not going to put theta, I'm going to put alpha. Remember, these are identities. They work for any sort of angle, so it doesn't matter what the angle is called. We can put anything in sine or cosine. Okay. So what I've done is I've just found an identity that uses just sine and just cosine, and I want to get sine, well, by itself, right? So why don't we do that? Okay. The trick here is we're going to solve for sine of alpha. We want to get that by itself. Well, what can we do first to get sine by itself? Yeah, subtract cosine squared on both sides. Okay, so on the left-hand side, I'm left with sine squared of alpha. On the right-hand side, I have 1 minus cosine squared of alpha. Okay. All right, sine is almost by itself. What can I do on both sides to get it completely by itself? Good, square root. Square root is the opposite of square. So taking the square root of both sides, we have sine of alpha equals, oh my goodness, that noise. The square root of 1 minus cosine squared of alpha. Am I forgetting something? Plus or minus, good. Okay, now we got sine by itself. We're actually not done yet. It looks done, but let's take a look at what the question says again. It says, let alpha represent an acute angle. Let's talk about acute angles. Acute angles look like this, right? They're definitely not bigger than 90 degrees. So I guess what we can do is we can imagine this angle being on a right triangle, like this. Right? We can imagine alpha being the corner of a right triangle. Now, when we've talked about right triangles, was sine, cosine, tangent, any of those values ever negative? No, right? All of those values were positive, right? So I guess sine of alpha, if it's acute, has to be positive, okay? So whenever you see in your question that alpha is an acute angle, all this is saying is like whatever you're trying to find is going to be positive. So acute basically translates to positive. Okay, so what we're going to do for this answer is I'm just going to scratch out the negative sign, and my answer is the positive square root of 1 minus cosine squared of alpha. Okay. Oh yeah. Yes. Oh, for the quiz, I might just give you some of the identities on the quiz, since you don't have to memorize it for the test. Yeah, I might just do that. I'll take a look at what I'm gonna do, but I'll either give you the identities or let you bring a new card. All right. What was I talking about? Oh yeah. Okay. So basically, your answer is the positive version. Not too bad, right? We just started out with a Pythagorean identity and we just solved for sine. Okay. Any questions? All right. Try example 3 on your own. Before you start, though, I want you to change cosine alpha into cosine lambda, okay? Because they were supposed to match. Okay. I just made a typo there. All right. I'll give you a few moments on this one. Very similar to part 1 or to example 2. Up on the board. Stephen, do you want to take us through this one?
So pretty much the same thing we did last time, but we put in cosine instead of sin. I was solving for cosine instead of sin.
Awesome. Yeah.
Just opposite of what we did last time.
Yes. Yeah, perfect. And it ended up being positive. All right. I don't know. It's actually called sine, not.
Oh, sorry.
Yeah. I just thought that was kind of funny. Sometimes I do call it sin in my head. All right. Sounds good. I actually didn't start example 4 yet in my last class, so I think I'm gonna leave that for next time. Now, if you look at your homework and you see something that looks like example 2 or example 3, you might want to wait until tomorrow because example 4 and example 5 are going to be a little bit more like that one, and we're doing something a little bit different. So just a warning on that. But I will see you tomorrow. And have a great, nice, warm day.